So it's a pleasure uh, to introduce Professor Raluca Scarlat uh, to the CSAC seminar, to CSAC. She'll be speaking to us, as the title indicates, on advanced nuclear technologies and the global um, solution. A little bit of background. Professor Scarlat is an assistant professor at the University of California, Berkeley. Previously, she was at the University of Wisconsin in Madison. She has her PhD from UC Berkeley, uh, and she has a rather broad research portfolio. At one end, I would say, is very scientific studies of the chemistry, electrochemistry, and physical chemistry of high temperature inorganic fluids. And at the other end, safety analyses, licensing, and design of nuclear reactors, and even engineering ethics. So it's a pleasure to have you here, and turn it over to you.
Thank you very much for the introduction, and thank you for the invitation to be here. I'm very glad to be here to give this talk. As Ron said, I work on molten-salt chemistry, and also I think a lot about advanced nuclear technology and the technological risks and the technological challenges of developing advanced nuclear reactors. And I should start with what motivates my work. If we think about the energy density of nuclear power, we could compare it in terms of scale to the BP oil spill that happened in 2010 in the Gulf of Mexico. About 5 million barrels of oil spilled, which is equivalent to only 1 day of US energy usage. If we were to look at what would be the volume of mined uranium ore, that would be equivalent to 1 day of US energy usage. That volume is about 6 barrels equivalent of uranium ore. So the energy difference between fossil fuel and nuclear energy is staggering. You go from order of magnitude of million to order of magnitude of 1. And so to me, that seems, that is my motivation to continue to work on nuclear energy, because the energy density also translates into the byproduct of energy generation. Any technology will have byproducts. And so if we burn fossil fuel, the byproduct is CO2 and it's released into the atmosphere. If we burn uranium fuel, the byproduct will be fission products, which are solid and contained and of a much smaller scale. And so this this preface is to say that I'm not here as a nuclear energy proponent. I think that there are also a lot of challenges with nuclear energy and a lot of ways in which it can be made better. But there's a strong motivation to try to fix those hurdles. And so I'm going to speak about some of the hurdles to developing better, newer nuclear power plants for the world and for the US. I'll start with a map of the US and the current nuclear power plants in the US. You will notice here the in red are the ages of the power plants. The age is 49, 50 years old, 40 years old, 49 years old, 41 years old. So 40 years ago is when we built most of the power plants that operate today. This means two things. We've lost the habit of how we can build nuclear power plants. And by habit, I mean both the technological know-how of how to quickly build a nuclear power plant, although arguably we never built nuclear power plants quickly. And we've also lost the habit from the point of view of licensing and policy of developing innovative nuclear technologies. So to show you again a bit the timeline of power plant construction in the US, this is 1966. The first few power plants were beginning to be built. By 1973, most of them had been built. Then by 1985, if you compare 1985 to 2014, there's really not much difference between these plants, except that some of them had decommissioned and closed down. So after a hiatus of a few decades, we turn now to nuclear as possibly a solution to climate change, as possibly a solution to no carbon emitting energy technology. And the question we ask ourselves is, do we still want to build the same technology that we built in 1973? Or have there been advances in technology since then? And while there was a hiatus in construction of nuclear power plants in the US, there was still ongoing research on advanced nuclear reactors. And what we mean by advanced nuclear reactors is reactors that are typically not cooled by water. So conventional nuclear power plants are cooled by water, whether it's pressurized water or boiling water. They're cooled by water. Which means that they run steam turbines with their corresponding efficiency. Now, if we shift to coolants that can tolerate higher temperature without a very high pressure, or in general, coolants and fuels and materials that can tolerate a high temperature, that opens the door to other types of power conversion cycles, such as CO2 or air Brayton, that enable higher efficiency for energy conversion from the thermal energy that nuclear produces to the electric energy that we consume on the grid. It also opens the door to higher energy for high temperature applications in the chemical industry and in the manufacturing industry. So it broadens the market to which nuclear can sell its energy. And so the driver for the past few decades in research has been, to some degree, to push towards higher temperature nuclear reactors. Water reactor, to give you an idea of scale, water reactors operate at around 300 Celsius. That's not much hotter than your maybe oven at home or pressure cooker at home. Nuclear reactors, one could make an analogy with pressure cookers because they build up steam in a pressurized vessel. And then the push has been towards higher temperature operating reactors. A molten salt reactor might operate up to 700 degrees Celsius, 800 degrees Celsius. A gas-cooled fast reactor might have, or a gas-cooled reactor in general, might have an outlet temperature that goes even higher, and again allows something like hydrogen production or a higher efficient turbine to be used. The other motivations for development of these technologies were also sustainability of the fuel cycle. So both conventional nuclear power plants and the prior legacy activities of nuclear material generation for defense applications have generated an inventory of transuranic materials that we store today with no current use for them, such as americium and curium and some of the plutonium. And so we could devise what we call fast spectrum reactors that burn these side products of nuclear reactors. And so there's been quite a bit of research on fast spectrum reactors, whether they are liquid metal cooled or gas cooled reactors. So in that case, the motivation of the research was the ability to recycle previously used nuclear fuel. And I mention this because it's really important in the current context to understand what changed in the last 10 years. What changed was the motivation for development of new nuclear technology. While the focus in the past had been on closing the nuclear fuel cycle and recycling spent fuel, and on pushing to higher temperature in order to be able to use nuclear in the petrochemicals industry. Today, the focus has shifted towards cost. Can we make nuclear energy cost competitive with fossil fuel? And this shift towards cost and towards, do we have a business case for nuclear energy, is what inspires a lot of the startup companies that work on commercialization of a lot of these technologies that we see here. So then you'll say, but in the past few decades, we have been studying and the world has been studying all of these technologies. So what's different today? Well, the way that the technology development choices are being made today and the way that the reactor design is being simplified is very different from the way we had been thinking of it before when we thought about optimization of fuel utilization. Well, fuel utilization is not a concern today. We have reserves of uranium and thorium that will last us for hundreds of years of energy. So optimizing for fuel utilization in the next 2 decades is not the pressing concern. The pressing concern is, can we displace fossil fuel quickly enough to make a difference? And in order to displace fossil fuel quickly enough, we need to have a technology that's economically competitive. So this shift in motivation then changes how we develop the technology and the type of technology that's being pursued by startup companies. So I'll give you a few examples of startup companies around the world that are looking to commercialize molten salt reactors and salt-cooled reactors. And the difference between molten salt reactors and salt-cooled reactors is that the uranium or thorium fuel in a molten salt reactor is dissolved in the molten salt, so it's a liquid fuel that produces fission product and transuranic elements in the molten salt as a homogeneous mixture. In the case of a salt-cooled reactor, the fuel and the fission products and the transuranics are retained within solid fuel elements for the entire operation of the reactor. And the salt serves as a coolant to those solid fuel elements. It's very much similar to today's reactors that have solid metallic fuel rods and water coolant, but instead of the metallic fuel rods, FHRs would have graphite fuel elements in which there are microparticles that encapsulate nuclear fuel, and the microparticles are a composite of silicon carbide and pyrolytic carbon. And then the coolant, instead of water, would be molten salt. And so you'll notice that there are companies in the UK, Canada, a few companies in California, and other places in the US, as well as China has a program. Denmark has a couple of companies that are pursuing MSRs. And this is not an exhaustive list. There are other countries and other companies that are pursuing this technology. And so this is the appearance of these companies occurred over the last decade. And before the last decade, I would say it was really quite unthinkable that we would imagine a thriving startup ecosystem for molten salt reactors. We all thought that the technological hurdles would just be too high to move to an advanced reactors. But as Mark Twain said, they didn't know it was impossible, so they did it. So to give you some more details of why did it seem impossible 10 years ago, here's an image of that might be representative of FHR technology. This is a liquid molten salt at 500 degrees Celsius, and some graphite spheres that are floating on the salt. So this is the concept of FHR. You would have graphitic fuel elements that are spherical, the size of a golf ball, and they float in the salt and move around the reactor continuously. Of course, this then will require technology to count and keep track of the pebbles and where they go, technology to fuel and defuel the reactor, and also an understanding of the salt coolant and its behavior with the material that it interacts with. So its behavior as it interacts with metals and its behavior as it interacts with graphite. And then molten salt reactors. A lot of the motivation for molten salt reactor has been thorium fuel. Thorium fuel is typically mined together with rare earth metals that are mined for the semiconductor industry, and it's a byproduct. And thorium is slightly radioactive, so it's a costly byproduct because it costs to store it. So first, there are large reserves of thorium all around the world, and secondly, it has a negative cost to use it. And so the question is, okay, how do we put thorium in a molten salt reactor, and why a molten salt reactor specifically? Well, thorium is not a fissionable element, it's a fertile element. That means that it needs to be exposed to neutrons, to absorb neutrons, to breed uranium-33. And then uranium-33 is what we burn in a nuclear reactor. And so if we have to take our fuel through this cycle of neutron irradiation and then burning, it would be convenient to be able to move it around the reactor so that it gets the right amount of neutron dose. And it would also be convenient for it to have a long lifetime, so that if we encapsulate thorium in a solid fuel element and we have to breed uranium in it and then burn uranium, well, that solid fuel element will have to last for quite a bit of time for it to be able to have this type of a lifetime. So the alternative is to dissolve thorium fuel in a molten salt and to transport the thorium, to online separate the uranium that is being bred and move it to the part of the core where we're burning, from the part of the core where we're breeding to the part of the core where we're burning. So molten salt reactors, because they have a liquid fuel, lend themselves quite conveniently to a thorium fuel cycle. Whereas in a uranium-235 fuel cycle, we don't have this need of breeding and then burning. On the other hand, we have the need of enrichment. That's that need is removed in the case of thorium, but we have the need of a liquid fuel. And so this is the second reason that molten salt reactors are being pursued, is to enable the use also of thorium fuel. That is not to say that molten salt reactors can't be used with uranium. They can also be used with uranium. So this all sounds great. We have so many technologies, so many technological options for advanced nuclear energy. So the question might be, why can't nuclear grow? We know how a nuclear molten salt reactor or a FHR reactor should work, so let's build it. Well, there are some technology risks. There are the question of cost, the question of developing the supply chain, and then there are, of course, the questions of licensing and culture. So I'll speak about technology, licensing, and culture for a bit. Here are some pictures that are representative of two challenges. On the left side, you will see a pot of molten salt with electrochemical sensors inserted from the top. So sensors and equipment and components is one hurdle, which ties into the supply chain as well. It also ties into technological hurdles. It is not, we do not have a broad set of options for measuring composition, for measuring temperature, for measuring flow rate, for measuring pressures. Because we are at high temperature, it is challenging to do so. And because we are in a liquid that we haven't worked with quite as broadly as other liquids, it is challenging to do so. So there are some technological risks around the components it would take to build a molten salt reactor. And then on the right-hand side, you see an image of the materials that are typically present in an MSR and an FHR. That would be graphite, which is used as a neutron moderator, the salt, and metallic alloys. And so there are questions around the corrosivity of the metal alloys. does salt corrode the metal? Or more importantly, can we predict the way in which salt corrodes the metal? Because if we can predict it, then we can engineer a system around it. And so in my group, we study the questions around the salt chemistry and how that helps us predict degradation of solid materials that come in contact with the salt, and how that helps us design sensors and distributed sensors for molten salt reactors. So I'll show you what these technological challenges mean in the context of licensing. When we think about licensing, the role of the nuclear vendor is to demonstrate to the regulator that their safety approach is acceptable. And we can think in terms of the risk triplet. And the risk triplet includes scenarios, probability, and consequence. So we have a class of scenarios that we designate anticipated operational occurrences. They are of high probability but very low consequence. Design basis events are what would be of medium probability, so they would occur once in the lifetime of a fleet. And beyond design basis events are events that would not be predicted to occur within the lifetime of a fleet of 100 reactors. So what I want to draw your attention to are the error bars around each of these scenarios. So each of these scenarios, we can envision that there's a tsunami and we lose power and the pumps no longer work. And so we have to predict, does the reactor overheat or does the reactor overcool in this case of molten salts? And does that overcooling lead to damage of any of the materials? And does that damage of the materials lead to any release of radioactivity? So this is what you see on the x-axis is release of radioactivity, and you notice the error bars. And the biggest challenge with new technology is not where the scenarios lie on this frequency versus consequence plot relative to the limit of acceptability. Usually the scenarios lie quite far, which is why advanced reactors are so attractive. The low pressure operation of a molten salt reactor system makes it much easier to make the case for low consequence of events. If there is no stored energy available to disperse radionuclides because the system is operating at low pressure, then we would expect that scenario of a vessel breach or a pump shutdown to be quite far away from the limit of acceptable release. But the challenge with so while new technology lies far away from the limits, it has high uncertainties because the data availability is much lower for advanced reactors. And so the challenge is the size of the error bars. And it's on the one hand a licensing challenge. On the other hand, it's also a challenge for the startup companies because they have to manage that technological risk of not knowing how far exactly they are from the error bar. And one way to manage it is to say, well, I'll just move even further from the limit. And that might be possible to do with advanced reactors. So this is the technical part of the licensing challenge. The other part of the licensing challenge has to do with the institutions that regulate nuclear energy. So I'll give you two examples from the US, but the same challenges would be faced anywhere around the world. There were two acts passed recently that point out some of the licensing challenges with advanced reactors. In 2018, the Nuclear Energy Innovation Capabilities Act enabled for cost share called for cost share for the fees to the Nuclear Regulatory Commission. And this is very important because the first MSR reactor that will be licensed will bear most of the uncertainties and most of the costs of licensing. And then the subsequent molten salt reactors that will be licensed, and you saw that there are many startups, maybe some of them will succeed, the subsequent licensees will have probably more certainty around their licensing path and probably lower costs. So the US government acknowledged this hurdle of the first of a kind licensing and then set up this program for cost share of that first of a kind. The other type of hurdles with licensing are reflected in the Nuclear Energy Innovation and Modernization Act that was passed in January 2019. So if one of the changes this act made has to do with the funding structure for advanced reactor licensing. Because the Nuclear Regulatory Commission recovers its cost of operation from fees that it charges to existing nuclear power plants. So if the costs that if the expenses that the Nuclear Regulatory Commission needs to put towards developing a licensing path for advanced reactors comes from the conventional nuclear industry with which the advanced reactors is competing, there's really very little incentive for the NRC to develop that capability to license advanced reactors. And so this, I make no claim as to whether these acts are going to be effective or are not going to be effective, but I am pointing to them as examples of what is perceived as hurdles to licensing advanced reactors. And so the first hurdle was, how do we motivate the NRC to think ahead of what is the infrastructure that they need to have in order to license something other than water-cooled reactors? The other element of the 2019 Act was development of a process for licensing advanced reactors and integration of risk-informed licensing. So I've shown you this plot. This is what we refer to risk-informed licensing. We think of scenarios that the nuclear reactor system might experience, and then we calculate the probability and the consequence. So one might think, is there another way to license a reactor but to think of scenarios and to think of consequence? And yes, there is. That's called experience. And for light water reactors, there are deterministic rules that will tell you the wall needs to be yay wide and you shall be okay. You do not need to do all of the probabilistic analysis in order, you need some, but not all of the probabilistic analysis to license a reactor for which there is a large experience base. And so this request of the Act to integrate risk-informed licensing into its licensing process is very important to encouraging innovation, because it does not rely on prior experience. It relies on engineering data and the understanding of our current understanding of the technology. And then the last and very important point that I outlined here is the staff. The staff and the knowledge of the institution about the new technology is essential to licensing a technology, because their role is to be an independent evaluator of the safety evaluation. And they can't be a knowledgeable independent evaluator if they don't understand the technology. But the technology is new, so we have a chicken and egg problem. How are they to learn ahead of time the technology and to learn it independently when the technology is currently being developed by the startup companies? So this is an interesting challenge. It's not unsurmountable, but it's acknowledged here in this act. So I talked about some of the technological challenges, some of the licensing challenges, and I'll talk very briefly about the cultural challenges. This is an excerpt from a report by the National Diet of Japan on the Fukushima nuclear accident that occurred in 2011, and this report was published in 2012. And he provides harsh criticism on the mindset that led to the Fukushima accident. And what is interesting to remember is that the reactors at Fukushima were GE reactors, and therefore US technology. And with the technology comes a safety culture, because the technology is operated and maintained and upgraded by engineers. And engineers need to have a safety culture to ensure that the technology is inspected and upgraded and operated properly. And that safety culture was exported with the technology. We didn't just export the technology, we exported the safety culture, and there was an assumption that that safety culture would be just as readily adopted as the actual physical hardware. And we learned from the Fukushima accident, for example, that process of exporting a safety culture into a different societal culture is not so easy. And it's not so obvious as to whether that was successful or not. So in this report, the chairman gives an example of the fundamental cause are to be found in the ingrained conventions of Japanese culture. So as we think about deploying molten salt reactors around the world in order to displace fossil fuel, coal, and natural gas around the world, we also have to think about, well, how do we export the safety culture of the molten salt reactors around the world? Because we will have to have a diversity of products, in a sense, a diversity of safety cultures that are developed, that are compatible with the diversity of cultures in which they lie. So this is an important challenge to manage. And lastly, another element of culture is the technology impact on society. And this is a picture of a book that is titled Radiation Brain Moms. And it speaks again about the Fukushima accident and how the women in Japanese society had the responsibility for child rearing and for providing the food for the children, whereas the men primarily were working at the nuclear power plant and working in the industry. And so there was a challenge in creating a dialogue between the women that were concerned about the food health, the food safety that was being fed to their children, and a dialogue between the women and then the men that were working in the engineering companies, providing the data to say this is safe. And furthermore, this was this split in this lack of dialogue was maybe arrived at by some of the decisions by the Japanese government to discredit the voices of these women. Now, whether these women were technologically right or not is not relevant in any way. The important thing is that the question was being asked, and the government was taking decisions to discredit, to discredit that question, for example, by creating this label of radiation brain moms, which was saying that these women's ability to make decisions was being impaired. And so as we think about more broadly developing nuclear technology across the globe, we also have to think of how does that technology fit within the cultural context. And so with that, I very much look forward to the conversation.